Okay, so we'll continue with the second lecture of the topic aromatic substitution reactions, electrophilic aromatic substitution reactions. Now we are going to talk about substituted aromatic rings. Yesterday we talked how it happens on benzene ring. Okay, so now basically you have to understand on the benzene ring two types of substituents can be there. One which pumps the electrons into the benzene ring, other one withdraws the electron from the benzene ring. So if some group is pumping the electron in the benzene ring, it makes the benzene ring more reactive towards electrophilic substitution reaction. Understand, it is electrophilic substitution reaction. So electrophile E plus comes and the electron chlorobenzene ring attacks. So if some group pumps electron, it increases electron density on the benzene ring. So it increases electron density on benzene ring, so it becomes more reactive. It will react faster with the E plus, right? So understand this between ring activating and ring deactivating group. Ring deactivating groups are show either minus I or minus R effect. Ring activating group shows either plus I or plus R effect. They pump electron, right? So we'll just give some example. This is not some great table, but just example. We always take this benzene as reference. So if somebody pumps electron, imagine CH3 pumps electron through inductive effect. Though it is small, but still it pumps electron, it makes it more reactive than benzene. When you take OCH3, now oxygen is electronegative. Oxygen pumps withdraws electron through minus I effect. But minus I effect, as you know, is much smaller compared to plus R effect. Okay, so it pumps electron through plus R effect, and this one is much more stronger than minus I effect, and therefore it is a stronger pumping group, and therefore it is more reactive than even toluene. This one is called as anisole. When you have benzene on that OCH3, it is anisole, and when only CH3 there, it is toluene. Okay, so understand this part. Though oxygen is very electronegative, second electronegative element in the periodic table, it shows very strong minus I effect. After fluorine, second most electronegative atom is oxygen, but still there is no comparison between resonance and inductive effect. Resonance effect is much stronger than inductive effect, and therefore it is still a pumping group and much more strong activating group. Whereas if you see withdrawing group, something like CHO, or you can have esters, C11OOR prime, all these are withdrawing group. They withdraw electron like this. Okay, they withdraw electron like this. So since they withdraw electron, they are they show minus R effect, so it is ring deactivating group, and therefore it is much less reactive than benzene ring towards electrophilic substitution reaction. If this will take 1 hour, this will take 5 hours. If it happens at room temperature, this will happen at 100 degrees. Things like that. If you put nitro, you know, is the most powerful electron withdrawing functional group. So this withdraws very strongly, and you need real harsh conditions to carry on these reactions, and these are least reactive compared to benzene. It is very low reactive. Okay, so all that what I said is written here. Now whenever there is a pumping group, either by plus I or plus R effect, what I am trying to say is any ring activating group, they are ortho-para directing. So I have just given some examples like anisole we talked, it's the pumping group. So if you do nitration, so I am just revising you. Nitration is electrophilic substitution reaction. If you remember nitration, the electrophile is NO2 plus. Okay, it is NO2 plus. So if you have this, nitration happens. So since it is electron donating group, it is ortho-para directing. It will have ortho-nitro anisole and para-nitro anisole. Imagine if you are having toluene. Now toluene also pumps electron. Now one thing listen to this point very carefully. This ortho and para product, they are formed in equal amount, 1:1 ratio. Why? Because OCH3 pumps through resonance, and resonance does not depend upon distance. It will be equally effective in ortho position, it will be equally effective in para position, and therefore you'll get 1:1 ratio of ortho and para. See, somebody puts OCH3 and NO2 here and not here. That is also same thing. Ortho is this side also, ortho is this side also, okay? And para is only one. We are getting 1:1 ortho para position product. Whereas if you react, and this is Fiddle graph, alkylation reaction. Now CH3 pumps electron through sigma bond, through plus I effect, right? So it's not a very strong pumping group, but still it is activating. It will be more reactive than benzene ring, and apart from that it will be ortho para directing. So you get ortho methyl toluene, para methyl toluene. This is actually xylenes. This is called as orthoxylene. This is called as paraxylene. Maybe I should write it for you, okay? These are the commonness we have to know, okay? So now interestingly, if you see here, toluene is formed, ortho product is found more than para product. Why? Because inductive effect is definitely dependent upon distance. By the time it comes to para, inductive effect reduces drastically. Ortho product, it is much more favorable, much more seen, and therefore you get more of ortho product than para product when you are pumping only through plus I effect, right? And now this is the withdrawing group we talked about previously. So if you have withdrawing group, you do this reaction. This is a Fiddle graph acylation reaction. CH3COCl in presence of AlCl3. You get only meta product. This is another very important. When you are having ring activating group, it is ortho para directing, and when you have ring deactivating group, the reaction is meta directing. Okay, so because this is ring deactivating group, it will be meta directing. You are getting on meta position COCH3. Similarly, if you do bromination, since it is withdrawing group, ring deactivating group, it will be meta directing, getting bromination on meta, right? So in this chapter, till now what we studied is anything which pumps electron is ring activating group. Ring activating group is always ortho and para directing, and when you have ring withdrawing group, when you have ring withdrawing electron withdrawing group, they are ring deactivating group, and they are only and only meta directing, right? So whenever you have ring withdrawing group, electron withdrawing group, it can be either through minus R or minus I effect, but either way it will be only meta directing. That's what we saw. So these are the two things we studied till now. Reasons. So if you have something like anisole, you are having OCH3, oxygen pumps electron. When it pumps electron, it increases electron density in ortho position. You can see here. Then it comes here, you get negative on para position. Then you get negative charge on ortho position. You understand what is happening? What is happening is you are attacking it with electrophile. Electrophile means E plus. Always whenever think about electrophile, think about E plus. It wants negative charge. So you can see when there is a pumping group OCH3, it pumps through plus R effect. You are getting negative charge on ortho. You are getting negative charge on para. You are getting negative charge on ortho. You are not getting negative charge on meta. So now attack has to happen on E plus. So which is having more negative charge? Ortho or meta? Para or meta? It is always ortho and para and not meta. And therefore electrophilic substitution happens at ortho and para. See, OCH3 pumps electron, increases electron density. So ortho and para you get nitro group. So mechanism we have done previously. Once again we'll do. We know HNO3 plus 2 so forth. It gives you NO2 plus. This is the electrophile. So first attack we will show on ortho position. So this pumps electron. This comes here. You get NO2. You should show some amount of conjugation also. So this positive charge is there. So this comes here and this conjugation is there. And then HSO4 minus takes away this proton, comes here, and you get ortho product. Similarly, it can happen para product. This negative charge comes here. This electron pair comes here. So this moves here and this comes and attacks here. You have to understand what it is basically. It is basically, you can imagine a p orbital is there parallel. And here there is a p orbital and p orbital. So it pumps electron to the p orbital. So it pushes electron, you're getting negative charge here. Then this comes here and you're getting negative charge here. So basically you are able to pump electron on this negative charge, on this para position. So this negative charge attacks nitro. And HSO4 minus attacks and you get this, okay. It's always good to show the resonance structure. I did not show, but let me show it. Let me show for this one. Let me show for this one. So you are having OCH3 So you can show like that. Similarly, you can show from here also, and you get this like that. Okay. Next is Fiddle alkylation. Now you can very clearly see that it is pumping electron, increasing electron density on ortho and para. But when you have something like toluene, CH3 is there, alkyl pumps electron to inductive effect. Now how will you say that it increases electron density in ortho and para, not on meta? Because if it pumps, it should pump electron to ortho, then to meta, because meta is closer than para, and then para. So it should happen only on ortho and meta at the most, not on the para. Then for that also we have to talk about the mechanism. So let us look at the intermediate. So you are reacting CH3Cl with AlCl3 and you are getting this intermediate. Now imagine attack happens on ortho position. You are getting positive charge on this carbon of the benzene. This carbon of the benzene is called as ISPO carbon, ISPO, ISPO carbon. Okay. Now this carbon is directly attached to electron donating group. You could have shown same thing with the OCH3 anisole also. Okay, but that is what I showed is easier. But you can always show like this also, right? Now you are getting positive charge on ISPO carbon, and therefore here directly pumping group is attached on this carbon. So it pumps electron and reduces the positive charge. So this intermediate is stabilized. So when it is stabilized, what happens? Reaction will be faster. It's like this. You know, it's reaction coordinate. So reactant is there, product is there. So if the intermediate is stabilized, so this is the intermediate, okay? So if intermediate is stabilized, then you don't need much energy, little bit energy and reaction happens, because this one is stabilized. So here it is stabilized, and little bit means you need to heat also at room temperature will happen, and then product is formed, and therefore this is stabilized. Similarly, if reaction happens at para position, what happens? Attack happens on para, and you are getting positive charge here, and this pi bond moves here, and you are getting again positive charge on ISPO carbon. Now ISPO carbon positive charge is stabilized by this electron donating group. But when it happens on meta position, you see you are attacking here, you are getting positive charge here. This moves, it has moved here, positive charge came here, and then this comes here. So you are getting positive charge next to the ISPO carbon, next to the ISPO carbon, and then para to the ISPO carbon. But you are never getting positive charge on ISPO carbon. So it is not that stabilized. So it is not as stabilized at when the attack is in ortho and para position, and therefore attack happens on ortho and para position. Now when you have electron withdrawing group, so if you do some any electrophilic substitution reaction, here I am showing bromination. So bromination with a PBr3, you get attack only on meta position. You could have shown here or you could have shown Br here. Both of them are meta, so it's fine. Okay, meta bromination. Why? It is because of minus R effect, it is withdrawing. So you can see it comes here, you get negative charge, you get positive charge on ortho position. Then it comes here, you get positive charge on para position, and then it comes here, you get positive charge on ortho position. So you are getting positive charge on ortho and para position. And what you have to attack with? You have to attack with E+. Now this is ring deactivity system. So it's not that meta position is getting more negative charge. No. That's why it is less reactive than benzene. But at least it is not getting positive charge. At least the meta position is not getting positive charge. And positive charge is coming only to ortho and para. So ortho and para are highly deactivated system, and therefore reaction does not happen on ortho and para position. Rather the reaction happens on the electrophilic attack happens on meta position. Okay, I hope it makes sense. Similarly, if you see bromination, let us see the mechanism. Now bromination is happening, so you get a positive charge on para, so it is being stabilized. It is being stabilized. One interesting thing is attack is happening on meta position. You are not getting positive charge on ISPO carbon. If positive charge would have come on ISPO carbon, If positive charge would have come on ISPO carbon, it will become highly unstable because nitro pulls electron. Understand? And we saw when attack happened on ortho and para position, like when it happened on para position, you are getting positive charge on ISPO carbon. So imagine if nitro was there and attack happened on para position, you are getting positive charge on ISPO carbon. So nitro first of all wants electron, and instead of giving it electron, you are giving it positive charge. Somebody is thirsty. Nitro is thirsty, it wants water. Instead of giving water, you are giving it more sun heat. So you are making it more and more thirsty, more and more unstable. And therefore, when nitro, any electron withdrawing group is there, attack does not happen on ortho and para position. Attack always happens on meta position, so that you don't get positive charge on ISPO carbon. Similarly, you can see this when you do sulfonation, attack happens on meta position, right? So these are the kind of intermediates which are formed. So mechanism you have to draw. So this one comes and attacks bromine here to get positive charge, and then next step again this H is taken away by Br minus, and you get this bond comes here and you get aromatic ring back. And these are the structures which you are expected to show that it is conjugated system, right? Now some exceptions we have to do. If you have aniline, this is called as common name is aniline, you have to know this, okay? So on benzene ring NH2 it is called aniline. So when you do electrophilic substitution reaction, you get electrophilic substitution on all the three positions at one step. You don't get separate ortho and para product, you get tri-substituted product ortho para. So it is 1. If you give the numbering, it is 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5 and 6. So you get 2,4,6 trinitroaniline. The name is 2,4,6 trinitroaniline. Why it happens? Because nitrogen, is less electronegative than oxygen. So it pumps electrons much more strongly than OCS3. You saw OCS3, oxygen is electronegative, so it holds its electrons. It does not give so easily. But nitrogen less electronegative. Its lobe is very big, okay? Much bigger than oxygen. So it overlaps very effectively with this carbon p orbital, and because they overlap very effectively, it pumps electrons more effectively. And then ortho and para position, you are having lot of electron density, and therefore you get tri-substituted product. But imagine I don't want tri-substituted, I want only ortho product or para product. I want to stop that. So what do we do? I need to make this aniline less reactive. Okay, all that I told is written here. I sent you the note. So what I want is, I want this reaction to happen. I want only a ortho and para position. So what I need to do is, I need to make it less reactive. I don't want full electron density to come on benzene ring. I want it to be distributed, less electrons available on nitrogen. So I'll make it amide. I'll react with CS3COCl, and second step we put some base also, mild base, okay? So something like generally you would have used something like pyridine. If you use pyridine, pyridine is a mild base. It will pull away the proton, you get this reaction. Now what is happening, understand? Now this electron pair on nitrogen, it is not completely coming to benzene ring, it is going here also. Initially whole electron pair of the nitrogens are available for benzene ring. Now it is not completely available for benzene ring, it is going here also, and little bit whatever is left is getting here. So it is still a ring activating group, which is much less activated than aniline. And now once you form this amide, you do reaction. I am showing a nitration. You could show any electrophilic substitution reaction. When you do nitration, you are getting ortho and para product separately. But I want NH2 only, so I need to hydrolyze this back to NH2. So you react with H3O plus hydrolysis. This amide will go back to NH2. This amide will go back to NO2, and you are getting ortho and para product. Okay, you are getting ortho and para product. So this is one of the interesting case. Second, now if it is disubstituted, what happens? So imagine you are having OCH3 and CH3. Now between OCH3 and CH3, which is stronger pumping group? Of course OCH3, because it pumps electron through plus R effect, and this pumps electron through plus I effect. There is no comparison between plus R and plus I. Okay, plus R is much stronger than plus I. So this one pumps electron, and therefore this will determine the product. So when I am doing halogenation, chlorination, Cl2 FeCl3, product will be formed ortho to this and para to this. We are not bothered about this. So it is coming ortho to this. Actually, if you look, this is meta to CH3. It's not stable, but this one you can forget because it's stronger pumping group, and this will determine the outcome of product. So you're getting ortho here and you're getting para here, right? Similarly, if you put here, again this will determine, so ortho and para, and it will not come here anyway, it won't come here, but here also product form is negligible because this is hindered. This carbon is ortho to this also, ortho to this also, looks quite favorable, but still this is hindered because of OCH3 and CH3, you know, electrophile approach here is hindered, and therefore electrophilic substitution here will happen, like in product will be something like 5%. Most of this will be this, so it will be 45 or 47%, 5% will be this, right? So when you do this reaction, so here there is no problem. Ortho to this is para to this, para to this is ortho to this. Only thing I wanted to show you is here is the electrophilic substitution happening here is really low. And imagine this last also, when they both have para to each other, when you do nitration, so para is blocked for both of them, so only ortho position is free. So ortho to this reaction will happen to ortho to this and not to this, because this will determine the product, and you are getting nitro product. Now when you are having withdrawing group, so I told you nitro is the most powerful withdrawing group, and you are having CHO. Now we know when a withdrawing group is there, it's meta directing. So we'll forget about CHO, we'll remember only and only nitro. So when nitro is there, nitro will determine where the product will form. So product will form meta to nitro. So meta to nitro is this also, meta to nitro is this also, right? Now these are two different products. So now we are doing Fiddle alkylation. So you are getting alkylation, methylation here and methylation here. Of course this will be major product because this place is little sterically more hindered than this one. Here CHO is there, so it blocks this place to a certain extent, and therefore it will not be great difference. It will be like 60-40%, but still you can see this will be major product, this will be minor product. All this which I am telling is small, no, like this will be minor, major. This is what question they ask in the all competitive examination. So you should know when this is there, this place is hindered, and therefore this will be minor, though it may not be much in product, but this is what they ask in competitive examination. Similarly, if you do this bromination, reaction will happen meta to nitro and not meta to CHO. Product will not form Br here, product will only form here because only nitro will determine. Now interesting thing is, if both pumping and donating group is there, then only and only pumping group will determine, because understand what is pumping is activating and withdrawing is just deactivating. So it will not determine if something is there which is activating the group. So understand, CH3 pumps electron through plus I effect, very weak activating group, very weak activating group, whereas this is a very strong deactivating group. But still this will not determine the outcome. Outcome will be determined by this. So if you do sulfonation, you get ortho and para to CH3. So you are getting ortho to CH3, para to CH3, and we talked previously that ortho is more favorable than para because plus I effect is more seen on ortho position than para position. And again this also is ortho, so here also it can happen, and it will happen little bit, but again product will not be more than 5%, negligible, because this portion is blocked by CH3 and NO2. I hope I make sense. Okay, so when pumping group is through plus I, ortho product is more formed than para because ortho group is more activated than para because of distance. Okay. Now exceptions. Halobenzene. This is very interesting case. So when you are talking about halobenzene, we are not talking about fluorobenzene. Fluorobenzene is orthoparadirecting, and it is ring activating also, because it pumps electron through a plus R effect and very strong plus R effect. But when you see chloro, bromo and iodobenzene, okay, when you see chloro, bromo and iodobenzene, it is ring deactivating yet orthopara directing. What I mean to say is, ring deactivating means this reaction is much slower than benzene ring. Benzene ring the reference. So halobenzenes are much lesser reactive. Halobenzenes are much lesser reactive than benzene when you are doing electrophilic substitution reaction. Okay, this one is less reactive, this one is more reactive. Clear? And now when this is less reactive, the question is, why is it less reactive? So of course, and why is it orthoparadirecting? So it is less reactive because it has to be ring deactivating. Now chloro, bromo and iodo, we know all these are halogens, the electron withdrawing group. So they show minus I effect. They show minus I effect, that's why they are ring deactivating. And why it is orthopara? That is very interesting, why it is orthopara. Because still it has plus R effect. It pumps electron. If it is chloro, bromo or iodo, all of them have lone pair. So it attacks here and this comes here, and you are getting ortho and para negative charge. So it is still orthopara directing. So if it is orthopara directing, we know for sure, I told so many times, there is no comparison between a resonance inductive effect. So if it is resonance effect is there and it is showing plus R effect, and then minus I effect is there, then plus R effect should be much stronger than minus I effect. It should be orthopara directing. Why the hell here is minus I effect stronger than plus R effect? That is interesting question. If you see, when we talked about anisole was having, if you talked about anisole was having all these effects which I talked about halobenzenes. This also pumps electron through plus R. This also withdraws electron through minus I. But here plus R is stronger than minus I. But in halogens also, in chlorobenzene, let us talk about chlorobenzene. Here also it withdraws electron by minus I, and it pumps electron through plus R. But it is ring deactivating system. That means here minus I is much stronger than plus R. And because of plus I it is orthoparadirecting, but minus I is stronger. Why? You can say, okay, because maybe halogens are more electronegative. No. Oxygen is more electronegative than all the halogens except fluorine. It is because, this is where it becomes very interesting. If we see chlorine, what's the atomic number? Chlorine is 17. So it is, chlorine is 17. So it is 287. So this is 1s2, 2s2, 2p6, 3s2, 3p5. So this lone pair of electrons is in 3p orbital. Similarly, if you see bromine, this lone pair is from the 4p orbital, and in iodine it is from 5p orbital. But carbon has only 2p orbital. When it was oxygen, it was 5. It was fine because oxygen also had lone pair in 2p orbital. And so 2p overlap very well, and therefore resonance is very effective, and therefore plus R effect was way stronger than minus I effect. But here 3p and 2p, their energy difference is there and the overlap is not very effective, and therefore plus R effect is very weak. Minus I effect is stronger, and therefore it is ring deactivating system, and halobenzenes are less reactive than benzene, and still it is orthoparadirecting because it has very small plus R effect, and that's what determines. But fluorobenzene, you can know it is 2p orbital, so it behaves like anisole. So it is ring activating and orthoparadirecting, fluorobenzene. But chloro, bromo and iodo, they are ring deactivating yet orthoparadirecting. With this, I finished my syllabus for your second semester. Please like and subscribe my channel. Thank you.